Hello viewers, Wagdaruna taking you through the story for A-Level Physics Paper 1. And this video I'm going to go through the marking guide for test 3, which was on conduction, convection and radiation. So where necessary, the following constants would be used. So now shall start with question 1. Question 1 part A Roman 1 says, what is made by conduction of heat? So here we shall see that conduction of heat is the flow of heat through matter from hotter regions to colder regions without movement of matter as a whole. So alternatively, you can say that this is the process of heat transfer through matter from regions of high temperature to those of low temperature without the bulk movement of matter. So both definitions are the same, it's only the language which is a bit changing, but they all are okay. Now let's go to Roman 2. So Roman 2 says, explain why mercury conducts heat better than water. So here we shall first say that mercury has free electrons capable of transferring energy without any part of mercury moving, while water has no free electrons. Also, the atoms of mercury are closer, allowing conduction by atomic vibrations, while atoms of water are further apart. So basically that's how marks would be awarded. So now shall go to part A Roman 3. Roman 3 says, explain the occurrence of land and sea breezes. So one, we need to remember that land breeze occurs at night. Therefore, we shall come and explain that at night, the land cools faster than the sea. Why? Because sea is heated to greater depths during day than the land. Now, as a result, the hot and less dense air above the sea rises up and is replaced by the cooler and denser air above the land. So that was land breeze. What about sea breeze? Sea breeze, we need to remember that it occurs during day. Therefore, we shall come and say that during day, the earth is heated to higher temperature than the sea, as the water has a higher specific heat capacity than that of the land. So as a result, the hot and less dense air above the earth rises up and is replaced by the colder and denser air from the sea. So that is how the marks would be awarded. So now we shall go to part B Roman 1. So B Roman 1 is, so it says that a copper sphere of radius 7 centimeters and density 900 kilograms per meter cubed is heated to temperature of 127 degrees Celsius. And then transferred to an evacuated enclosure whose walls are at a temperature of 27 degrees Celsius. calculate Roman 1 the net rate of loss of heat by the copper sphere. So now the surface area of a sphere is 4 pi r square. Now the radius was 7 centimeters, but has to be converted to meters. That is why you see here 0.07 as the radius. The temperature, one temperature was 127 degrees Celsius, so it has to be converted to Kelvin. That's why you see here 400 Kelvin. Then the ones of the wall was 27 degrees Celsius converted to Kelvin to give you 300 Kelvin. So we know this formula that power loss, net power loss is equal to this constant, so Stefan's constant, area, cross-section area, in brackets it is temperature to power 4 minus T naught to power 4. Then we shall substitute. So this one is here, this one is here, this is here, and this is here. Now next is use a calculator and come up with the power which was required. So now shall go to part B, Roman 2. Part B, Roman 2, they said calculate the temperature of the copper sphere after 5 minutes. And they said specific heat capacity of copper is 400 joules per kilogram per Kelvin. So mass of the sphere, we know that mass is equal to density times volume. So that means that the mass of the sphere will be volume of a sphere is 4 over 3 pi r cubed, and the density is given by that symbol. Therefore I come and substitute, because we are given the density which was 900 kilograms per meter cubed, then the radius 0.07, so when I substitute I'll come up with this when I use a calculator as the mass. Now here we need to note that it's average rate of heat loss. So average rate of heat loss will be equal to this which is here plus 0, which is the initial, over 2 to come up with, to be equal to the rate here in terms of quantity. So this is the heat quantity, MC change in temperature over time to get the power, to get this word rate. So now we have to substitute for M and the temperatures. So when I substitute, I'll come up with that. So this is the only unknown. So my aim is to make it the subject. So when I make it the subject, theta 1 will be equal to this degrees Celsius. So now I shall go to part C. Part C says, explain why heating systems based on the saturation of steam are more efficient than those based on the saturation of boiling water. So here shall come and say that a given mass of steam gives out more energy than an equal amount of water, and this is because of the high specific latent heat of vaporization of steam. So that is how the marks would be awarded. So now we shall go to question 2. Question 2 part A, Roman 1 says, what is meant by a black body? So we shall come and say that a black body is one that absorbs all radiations which fall on it without reflecting or transmitting any. So this last condition is vital. Now we shall go to part A, Roman 2. A, Roman 2 says, give 2 examples of a black body. So one is the sun, next is the stars, then black holes, and also an almost enclosed blackened surface or furnace with a small hole. So this word has to be seen. So that is how the marks would be awarded. So now we shall go to part B. Part B says, with the aid of graphs, describe how radiation emitted by a black body varies with wavelength of for 2 temperatures. So this time they want 2 temperatures. So we shall come and draw a sketch. Horizontal axis, label it. Vertical axis, label it. Then the first temperature, that will be the curve. Then second temperature, that will be the curve. So here we need to know, this one is very vital for you to know that as temperature increases, the graph also goes in that shape. So that will be the locus for maximum wavelength. So this lambda means wavelength, as you can see it here. Therefore, it implies that for this temperature T2, the maximum is here, and for temperature T1, the maximum is there. They also told us to explain, so that at each temperature T, the energy radiated is maximum for a certain wavelength, which is lambda max, which is this, which decreases with increasing temperature. I think realize that this for temperature T1 it was here, and for temperature T2 it is here, so it has reduced. Then we shall also come and say that as temperature increases, the energy radiated by each wavelength increases, but the intensity for shorter wavelengths increases more rapidly than that for longer wavelength, and so the body becomes brighter. Then next we also need to know that the area under any spectral curve is equal to the total energy radiated per second per square meter. So that is how marks would be awarded. So now we shall go to part C, Roman 1. So part C, Roman 1 says, define thermal conductivity. So thermal conductivity is the rate of heat flow perpendicular to opposite faces of a 1 meter tube of a material when the temperature difference across its faces is 1 Kelvin. So 1 Kelvin has to be seen, 1 meter tube has to be seen. And now we shall go to part C, Roman 2. So Roman 2 says, describe an experiment to determine the thermal conductivity of glass. So here we need a label diagram. So let's first draw a label diagram. To help us is the description. So you need to label, that is a steam chest, then steam in and steam out. Then that is a brass slab X, and that is a glass disc of interest, and also the brass slab Y. So these are the thermometers. So you come and say that the glass is made into a thin white disc, and its diameter D and thickness L are measured and recorded. So in this description, every parameter we are going to use has to be described. So now we know that D denotes diameter and L denotes thickness. And you realize that now the glass has been made in form of a disc, which is there. So we shall now say that the disc is then put between two brass slabs X and Y, which is this. And this is brass slab Y, brass slab X. each carrying a thermometer. So this one, brass slab X has a thermometer this, and slab Y has this thermometer. The next one is that the disc and brass surfaces are smeared with a thin layer of grease for better thermal contact, so that they are in contact. So before we go to the next slide, let's see the marks for this slide. So steam is passed through the steam chest until the thermometers T1 and T2 show steady values. So that word steady values is needed. Then the steady temperatures theta 2 and theta 1, theta 1 and theta 2 respectively are recorded. So theta 1 is from thermometer T1 and theta 2 is from thermometer T2. Then show that the disc is removed and slab Y is heated directly when in contact with slab X until its temperature is higher than that of theta 1. Is higher than theta 1. Then the steam chest is then removed and the disc is placed on top of slab Y. The temperature of the slab Y is recorded at suitable regular intervals. A cooling curve is plotted. The slope S of the graph at theta 1 is obtained. The mass M of slab Y of specific capacity C is determined. So this M denotes mass of slab Y and C denotes specific capacity of slab Y. The thermal conductivity K of the disc is then obtained from the formula that K is equal to 4mCSL over pi d squared in brackets change in temperature. So here they don't need the derivation of how this one comes about, so that is why you just quote it. If they want derivation, they will tell you, they will specify it in the question. So that is how marks would be awarded. So now we shall go to part D. Part D says radiation from the sun falls normally on a blackened roof measuring 20 by 50 meters. That is the area or surface area. If half of the solar energy, not this word, half of the solar energy is lost in passing through. So here it was error was missing. So passing through the Earth's atmosphere, calculate the energy incident on the roof per minute. Not this word, per minute, not per second. In brackets, they give you some constant. The temperature of the sun's surface is 600 Kelvin, radius of the sun is 7.5 exponent 8 meters, and the distance of the sun from the earth is 1.5 exponent 11 meters. So here I need to make a sketch for easy answering of the question. So this is the sun and this is the blackened roof, and this is the distance between the sun and the blackened roof, which would be taken as the distance between the sun and the earth. And the surface area is denoted by symbol AB. And this RS is the radius of the sun. So you can see that energy intensity, which is denoted by E int, is given by power of the sun over the distance over the area of this sphere. Now this one, you can see it as linear, but it is a sphere because this sun is a sphere. So even the distance from here to here will act as the radius of a sphere, because this sun radiates in all directions. But our interest is from here. Our interest is what radiates from between in this region from here up to here, but that doesn't mean that only radiates in that part, it's also radiates in these other places. So that's why you have to get the area or the surface area of the sphere, and surface area of that sphere using this as a radius is given by this ASB, and it's given by the formula 4 pi r squared. Now this power radiated by the sun has the formula that area, then this Stefan's constant, then times temperature of the sun raised to the power 4. I believe you know those formulas. So what you're going to do, 4 pi is going to cancel, then this one has no power, so it will first be pulled outside. Now this one, I think we realize that here the power 2 is outside, so this one it will become RS, but this is power 4, meaning that inside it will be t squared. Then this one is power 2, so it will just be RSB. Now we are given the question, so this one is a constant, it is known. Then this one was given radius of the sun. Then this one temperature of the sun was given. Then this one distance between the sun and the earth was given. So when you use a calculator, we shall come up with this. So in physics, it is in such questions, it is recommended that you use standard form to write your answers. So that was energy intensity. I think we realized that energy intensity is watts per meter squared, so it is per unit area. But we want for the whole of this. In other words, this is for 1 meter squared, but we want for the whole of this, so it will be this energy intensity multiplied by the total area of this surface. But remember, in the question they told us that it is only half which reaches the surface. That is why you see this a half. So if it was not mentioned in the question, this a half would not be there. But because in the question they told us it's only half, so that's why you put that a half. Therefore, you come and substitute. This a half was given the question. This one is the energy intensity, which you have calculated here, and this is the area of this surface, which is, remember, it was 20 by 50. So in the end, we shall come up with this as the answer, joules per second. So joules per second is another unit for power. And so in the question they told us they wanted energy incident per minute. They used that word per minute, but this is now per second, so we have to change it to per minute by multiplying by 60 to come up with this as the answer required. And that is how the marks would be awarded. So now we shall go to question 3. Question 3 part A says, explain the temperature distribution along Roman 1, a perfectly lagged metal bar, and Roman 2, an unlagged metal bar. So I shall say that for a perfectly lagged metal bar, no heat is lost to the surrounding. So when you know that, we shall come and say that the rate of heat flow along the bar is the same, making the fall in temperature along the bar to be uniform. So what about Roman 2 for an unlagged metal bar? So we shall come and say that for an unlagged metal bar, heat is lost transverse to the conductor. So transverse means if heat flows in this direction, it will be lost transverse in that direction. Like that. So what does that imply? It implies that the rate of heat flow along the metal is not the same, and hence the temperature gradient along the bar decreases with distance from the hotter end to the colder end of the bar. And that is how the marks would be awarded. So now we shall go to part B. Part B says, describe with the aid of a labeled diagram how an optical radiation pyrometer is used to measure temperature. So we need a label diagram to ease the description. So we show the rays from the source up to the observer. So that is how the rays are. So this is the very hot body, or it can be a furnace. So that means that an optical radiation pyrometer is used to measure temperatures of very hot bodies, for example, temperature of a furnace. That is the objective lens. Then that is the filament. This is the red filter paper. And this is the observer. That is the eyepiece. So this is a low power telescope. So after drawing the diagram, shall come and say that the setup is arranged as shown. This statement is to help you link this diagram to your content. So yeah, now come and say that the objective is used to focus the hot body so that its image lies in the same plane with the filament. As I think you can see here, this one, the point of intersection is at the filament. That's what they mean. Light from both the furnace and the tungsten filament lamp passes through the red filter to the observer's eye. I think we can see that here now the light from both the filament and this very hot body passes through the red filter to reach the observer's eye. Use it through the eyepiece. So before we go to the next slide, let's see marks for this slide. So now shall come and say that if the furnace is brighter, there are some conditions. So if the furnace is brighter than the filament appears dark on a bright background. However, if the filament is brighter than the furnace, then it appears bright on a dark background. So after knowing this, shall now come and vary the temperature of the filament by adjusting the current through it using the rheostat. Rheostat means variable resistor, until the filament and the furnace temperature are equally bright and the image of the hot body cannot be distinguished from that of the filament. At this point, the temperature of the furnace is equal to that of the filament. This temperature is read off from the ammeter previously calibrated in Kelvin. So in that way, the temperature of the hot body will have been got, and that's how the marks would be awarded. So now we shall go to part C, Roman 1. So C Roman 1 says state Prevost's theory of heat exchange. So you come and say that it states that when a body is in thermal equilibrium with its surroundings, its rate of emission of radiation to the surrounding is equal to its rate of absorption of radiation from the surrounding. Alternatively, you can come and say that it states that a body radiates or absorbs heat energy at a rate determined by the nature of the surface and the temperature of the surrounding. That was Roman 1. What about Roman 2? Roman 2 says a metal sphere of radius 1.5 centimeters is, so this word is suspended within an evacuated enclosure whose walls are at 320 Kelvin. The emissivity of the metal is 0.40. Find the power input required to maintain the sphere at a temperature of 320 Kelvin if heat conduction along the supports is negligible. So surface area of the sphere is given by 4 pi r squared, which is that. Therefore, and power input will be that, given by that formula, where this is now the emissivity, this is the area, that is the constant, Stefan's constant, and this is the change in temperatures. So temperature being radiated and temperature of the enclosure. So this is the emissivity, it was given as 0.4. Area we have been calculated as that. Then this constant is known, this temperature is here and this temperature is there, so the power will be 0. And that is how the marks would be awarded. So now shall go to part D. Part D says a metal boiler is 1.5 centimeters thick. Find the difference in temperature between the inner and outer surfaces if 40 kilograms of water evaporate from the boiler per meter squared per hour. Here they give us some constant that the latent heat of vaporization of water is that, and thermal conductivity of metal boiler is that. So now this formula, should dt is equal to Ka, change in temperature, over L. So this K is the thermal conductivity, is the area, cross-section area, and this is the temperature gradient. So this one can be given by, remember this is rate of heat, so it will be mL over T, where L is the latent heat of vaporization, mass, and time. Now when you substitute mass per second will be given by that, because 1 hour has to be converted to seconds. That's why you see 3600. Latent heat of vaporization was given as that, it was kilojoules, so we have to multiply it by 1000. Then this is thermal conductivity, area, cross-section area, temperature gradient. Here the change in temperature, we don't know it, but we know the thickness. Thickness has to be converted to meters. That is why here it was 10 meters, we multiply by 10 to power negative 2 to convert it to meters. Now my aim is to make theta, the change in theta, the subject. So when I do that, I'll come up with 6 Kelvin. And that is how the marks would be awarded. So now shall go to question 4. Question 4 part A says distinguish between diathermous and adiathermous objects. So diathermous objects are those that absorb little of the radiation passing through them, while adiathermous objects are those that strongly absorb radiation passing through them. So now shall go to part B, Roman 1. Part B, Roman 1 says a flux of solar energy incident on the Earth's surface is this. Calculate part Roman 1 the temperature of the surface of the sun. So let's first make a sketch to help us do the calculation. So like I explained under the roof, so these are two, this is the sun, this is the earth, and this radius is the radius of the sphere through which the sun radiates its energy. Remember, sun radiates in all directions since the sphere, but our interest is the one which reaches the earth, so we need only this fraction. So we shall come here and say that energy intensity is given by power radiated over area of this sphere, and of the sphere of which makes the orbit of the sun. So this power of radiated is given by that formula, I think you remember it. Then this area, surface area of the sphere, we shall use this as the radius. So when I try to simplify, I come up with that part. So before we go to the next slide, let's see marks for this slide. So substituting, we shall come up with that because we are given energy intensity, we have know this constant, and substitute will come with only this as the only unknown. So my aim is to make Ts the subject. So when I simplify, I'll come up with that. Then Ts will now be equal to that in Kelvin. So now we shall go to Roman 2. Roman 2 says, calculate the total power emitted by the sun. So power emitted by sun is given by PS, which is this formula. And now we know Ts, so we can easily substitute. So 4 pi is there, radius is there, this constant is known, and this temperature we have calculated it, so we can easily use a calculator to come up with the required power. And that is how marks would be awarded. So now shall go to Roman 3, part B, Roman 3. Roman 3 says, calculate the rate of loss of mass by the sun. So energy is given by this formula, mass defect multiplied by the speed of light. So we know, so that is energy, but therefore power will be energy over time from the definition rate of doing work. So this energy is here over time, so this energy is that multiplied by this as we saw it here, but then you divide by time. So this rate will now be equal to make this, bring this on this side to come up with PS over C squared. So when I substitute P, we have got it in Roman 2, this C is speed of light, and you'll be able to, so this is a constant, the speed of light is a constant. So you'll be able to come up with this when you use a calculator. So it's advisable to use standard form or scientific form in your answers. And that is how marks would be awarded. So now shall go to part C, Roman 1. So Roman 1 says, explain how heat is conducted through a glass rod. So you come out that when the glass rod is heated at one end, the atoms at that end vibrate vigorously about their mean position. But since they are coupled to their neighboring atoms by interatomic bonds, they pass some of the vibrational energy to them. These in turn pass on their energy to their neighboring atoms. The process continues, and through this chain of collisions, thermal conduction occurs from one end to the other. And that is how marks would be awarded. So now shall go to part C, Roman 2. Roman 2 says, why is a metal a better conductor of heat than glass? So shall come and say that in metals, heat is transmitted by movement of free electrons and by interatomic vibrations. But in nonmetals, heat is transmitted only through interatomic vibrations, since nonmetals don't have free electrons. Therefore, since electrons are very small and highly mobile, heat transfer due to motion of electrons is faster than heat transfer due to interatomic vibrations. Therefore, metals are better conductors of heat than non-metals. So now shall go to Roman 3. Roman 3 says, explain briefly why it is necessary to use a thin specimen of a large cross-section area in determining thermoconductivity of a poor conductor of heat. So here we shall say that a thin specimen of a large cross-section area is necessary because it provides measurably steep temperature gradient, and as a result, the rate of heat flow becomes measurable. So that is how marks would be awarded. And now we shall go to question 5. Question 5 part A says the diagram in figure below shows a device for detecting infrared radiation. So this is the diagram. Roman 1, what property of the liquid is employed in the device? So the property is that the liquid is volatile and highly flammable. Then Roman 2, explain how the device operates. So here we come and say that both bulbs contain a mixture of air and vapor of the liquid. Therefore, when infrared radiation falls on the device, the blackened bulb, which is a good absorber of radiation, absorbs more of the infrared radiation than the unblackened bulb. This makes the air vapor mixture in the blackened bulb to increase, causing it to expand and thus increasing the pressure in the blackened bulb. The increased pressure in the blackened bulb pushes the ether along the ether is the liquid employed, so pushes the ether along the tube, and this therefore shows the presence of infrared radiation. And that is how marks would be awarded. So now we shall go to part B. Part B says, describe briefly how a thermocouple can be used to detect thermal radiation. So still this can be easily explained with the aid of a diagram. So this is the infrared radiation, then that is the highly polished surface. That is the cold. These are the cold junctions shielded from radiation. This is the shield to prevent radiation from reaching the cold junctions. And these are the hot junctions. So red diagram with any 4 labeling, you could get yourself the 2 marks. So you can see that the setup is arranged as above. So this admit helps you to connect the diagram to your content. Then we shall come and say that one set of junctions of the thermocouple are blackened to make them good absorbers and then exposed to infrared radiation, while the other set of junctions are shielded from the infrared, as you saw in the diagram. When infrared radiation falls on the thermocouple, thermopile, the highly polished metal cone concentrates the radiation onto the exposed junctions of the thermocouples. The exposed junctions become hot while the shielded ones remain cold. A thermoelectric EMF, which depends on the temperature of the junctions, is generated and can be seen by a deflection on the galvanometer. So each time there's a change in temperature, there will be a thermoelectric EMF generated. Now since we have a hot junction and also a cold junction, there will be a change in temperature, and that is why this EMF is generated. So this shows the presence of infrared radiation, and hence they have been detected. And that is how marks would be awarded. So now we shall go to part C. Part C says, explain the greenhouse effect and how it is related to global warming. So you can see that radiations from the sun have short wavelength due to high temperature of the sun. When this radiation of short wavelength passes through the water vapor and carbon dioxide gas in the lower layers of the atmosphere, it warms up the lower layers of the earth. The earth will re-emit this radiation as a black body radiation of long wavelength because of the low temperature of the earth. The black body radiation will therefore be trapped by the water vapor and carbon dioxide gas in the atmosphere, thus preventing the radiation from escaping from the Earth's atmosphere. So this radiation, which has been prevented from escaping from the Earth's atmosphere, will therefore cause what we call global warming. So that is how marks would be awarded. So now shall go to part D, Roman 1. So D Roman 1 says, two cylindrical bodies A and B are made of the same material, but the length of A is twice that of B, and the cross-section area of B is a third that of A. If the ends of A and B are subjected to the same temperature difference, find the ratio of the rate of heat flow through A to the rate of heat flow through B. So you come here and say that since they said same material, it implies that thermal conductivity is the same. That is why here we should say that K1 is equal to K2 and let it be K. Then we're also given that the ratio length of A to that of B is twice. So length of B is twice that of A. We are told also that area of B is a third that of A. So that is why you see area of B being a third of that of A. So now we know that L1 over L2 is 2 and A1 over A2 is 3. So you come and say that the rate of heat flow through A is given by dQ1 dt, which is equal to, given this formula, Ka multiplied by the temperature gradient. Same that through B is also dQ2 dt, which is Ka2 multiplied by the temperature gradient. So when you divide these two rates, we shall come up with this, which is here, divided by this, which is here. And when you divide, you realize that this change in temperature will cancel. Then this K will also cancel. So you are going to remain with A1 over A2, which is here, and now this is 1 over L1 and this is 1 over L2. So the reciprocal becomes L2 over L1, which is here. So here we already know from the question that A1 over L2 is 3. And we know that L1 over L2 is 2, therefore L2 over L1 will be a half. When I multiply these two, I'll come up with 3 over 2. Therefore the required ratio is 3 to 2. And that is how marks would be awarded. So now we shall go to part D, Roman 2. Roman 2 says that in the determination of thermal conductivity of copper, when water flows round the cool end of a copper rod at a rate of 600 centimeters cubed per minute, its temperature increases by 3.3 degrees Celsius. The temperature at 2 points, at distance 5.2 centimeters apart, along the copper rod are 70 degrees Celsius and 30 degrees Celsius respectively. Find the thermal conductivity of copper if the radius of the rod is 1.2. So just that mass of water flowing per second is, remember, mass is volume times density. So because there is this word per second, you also have to add it here on one of them. So volume per second times density. So volume per second will be this. Remember, it was this. So you convert it to meters cubed. Because it was meters cubed, you convert it to meters cubed over per second. That is why you divide by 60. Then density of water is 1,000. So when I multiply these two, I'll come up with 0.01 kilograms per second. So you come and say that the rate of heat gained by water is equal to the rate of heat flow through the copper. Rate of heat gained is given by that, because now this is mass per second, and rate of heat flow is given by that. So Ka pi r squared is A multiplied by the temperature gradient. Then I'll come and substitute mass per second, specific capacity, change in temperature. Thermal conductivity, we don't know it, so this pi, then r squared, change in temperature, then thickness. So that means that I can make K the subject, and when I make K the subject, it will be this watts per meter per Kelvin. And that is how marks would be awarded. So that brings us to the end of this video. Thank you for watching, and bear in mind the next video will be on this marking guide for Physics Paper 2 Test 4, which is also available on this platform. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video with the marking guide of Physics Paper 2 has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so that we can all benefit as a family.